Hello everyone. Today I'd like to introduce the third chapter of the book named RFIC Module Design 1 MMIC Amplifiers. And I will introduce it from these two parts. Firstly is the basic theory of the MMIC amplifier, including description of the DC bias injection, classification, stability, and gain analysis, and different types of noise, such as thermal noise, shot noise, flicker, and popcorn noise. Transistors requires DC bias to operate. Set the operating point to display 1 to 5 characteristics, and the AC microwave signal fluctuates up and down at this value. And I will introduce 1 to 5 curve and operating points in details. Point 1 has low noise operating point. Point 2, VGS is close to 0 volts. ID is close to IDSS, providing the maximum signal gain, but high DC power consumption and increased noise make it unattractive. Point 3, the midpoint of the 1 to 5 curve, achieving maximum linear output power. Point 4, high efficiency but reduced linearity. And next is the application methods of the biovoltaic. Method is apply bias to the positive drawn voltage and negative gate voltage through parallel introductance. Method B is apply bias voltage to high value resistors suitable for most situations. Method C is short circuit the microstrip branch to ground and use the decoupling capacitors. Method D is self-bias technology, powered by a signal power rail, but with increased DC power consumption. Method E is active load technology, suitable for high density and DC coupled amplifiers. Method F is consistent current originates from bias technology, and the amplifier operators on IDSS. Method G is level shift diode technology for DC coupled amplifiers. Method H is standard bias configuration, increase source stabilization resistance. As shown in figure 3.4, a battery-powered communication terminal with a bias circuit using self-bias and stacked bias techniques about the on-chip coupling capacitor. Approximately 20 picofarad is usually not sufficient to ensure unconditional stability of frequencies below 1 GHz, and external decoupling capacitors and other bias circuits are required. Stability consists of two conditions. denotes as unconditional stability and conditional stability. In unconditional stability, the total circuit does not oscillate when any matching network or termination is added, whereas in conditional stability, the total circuit either can be stable and can oscillate under any condition. Figure 3.5 shows the stability circle on a Smith chart. At the output plane and the shadow region in figure 3.5 is the stable region. Figure 3.6 shows the circle of unconditional stability. And this is the method for improving stability. First is resistance loops. By adding small series resistors or large parallel resistors at the input or output terminal, the stability of transistors can be improved. Adding resistors creates a trade-off between noise and gain. Therefore, if adding resistors, the application specification must also be considered. Two is the second is feedback methods. Most amplifiers contain some form of feedback. Feedback can be negative feedback or positive feedback. In this amplifier design, negative feedback is applied. And several gain equations are used in microwave amplifier design. The transducer power gain Gt, the power gain Jp, and the available power gain Ja are designed as shown in the right picture. And figure 3.8 shows a general microwave amplifier diagram. And this part is the noise consideration. The first one is thermal noise. Thermal noise refers to the thermal disturbance of charge carriers caused by Brownian motion. The thermal noise power is directly proportional to the absolute temperature, manifested as white noise, and the noise power's spectral density is independent of frequency. The second one is short noise. Scattering noise originates from the particle-like nature of electronic charges and must have a direct current and potential barrier. Ordinary linear resistors don't produce short noise, and their characteristic is white noise. The third one is scintillation noise. The most mysterious type of noise, scintillation noise, which occurs in many phenomena such as cell membrane potential, Earth's rotation rate, galactic radiation noise, and transistor noise. The last one is popcorn noise. Another type of noise is semiconductors. In semiconductors is popcorn noise. And this type of noise was initially observed in point contact deduce, as well as in common junction and now deduce certain resistors and crystalline transistors in discrete and integrated circuits. And this section addresses the practical MMIC amplifier design. Three amplifier types are mentioned, including the IF amplifier, the low noise amplifier, and the power amplifier. About IF amplifier design, firstly is the introduction. The block diagram of cool band low noise block-down converter is shown in figure 3.10. The function of LNB is to convert satellite frequencies into the frequencies accepted by the set-top box. The main performance parameters include linearity, noise removal, frequency conversion, and amplification. Secondly is the gallium-indium phosphide characteristics. The design outlines 6-inch gallium-indium phosphide HBT high linearity technology with 4 emitter fingers. The typical working current is 50 milliampere, and the junction temperature is 150 centigrade. And thirdly is two-stage broadband IF amplifier design. The broadband IF amplifier is designed for cool-band LNB with a bandwidth range of 1 to 2 GHz, aiming to achieve flat gain in the broadband range. The amplifier adopts a common emitter configuration which stabilizes the bias point through voltage divider bias and emitter resistance, and adopts a loss matching network to achieve flat gain in the broadband range. Pay attention to the interstage matching network in the design to provide a positive gain slope and ensure stability, and the amplifier's schematics are shown in figure 3.11, and the most normal topology is the use of the resistors in series with matching circuits as shown in figure 3.12. Fourthly is the fabrication and measurement. Measure using JSG, probe and network analyzer. The simulation results shows that the DC power consumption is 3 volts with a consumption of 19 milliampere and a total power consumption of 57 milliampere. The gain is 27 decibel and the flatness is 1.5 decibel. The input and output return losses are 24 decibel and 12 decibel respectively. The picture on the right shows a microscopic photo of the layout and manufacturing of gallium-indium phosphide HBT. Broadband MMIC IF amplifier use the cadence tool. The simulation and measurement results are shown in Table 3.1. And this section demonstrates the feasibility of integrating image suppression filters into cascade low noise amplifiers for cool-band low noise block-down converters in direct satellite broadcasting systems, as shown in Figure 3.16. This cool-band cascaded LNA is manufactured for the first time on gallium indium phosphide, gallium arsenide phosphide (HBT) technology, rather than silicon germanium HBT and CMOS technology, and fully integrates tunable image suppression notch filters without the use of off-chip components. Its main features include excellent image separation ratio, easy turning, and minimizing the contribution of notch noise. In addition, this technology outlines on-chip based collector B2C junction diodes to achieve complete integration. The cascaded LNA shown in Figure 3.7 is designed using 6-inch gallium indium phosphide, gallium arsenide phosphide, high linear HBT technology, and the accurate large signal characteristics of gallium indium phosphide, gallium arsenide phosphide (HBT) are extracted using a vertical bipolar complementary model. The image north filter uses a base collector junction diode, and its turning range depends on the diode. The cascaded LNA model, due to its large emitter area, can minimize the base resistance and bias it with a current of 6 milliamperes. This bias current is selected to minimize power consumption and achieve low noise figure. By adjusting the DC control voltage, F notch can be centralized to compensate for process changes and possible turning, thereby determining the resonant frequency of the notch. The cascade LNA chip shown in the Figure 3.19 was fixed on a gold-coated Teflon substrate with silver epoxy resin and subjected to wafer-level probe testing. Figure 2.20 shows the 20 dB image superposition regional below 9.25 GHz, and Figure 3.21 shows the passband gain and noise figure response. Measure the 1 decibel gain compression point by changing the 12.22 GHz RF input power of cascade LNA between the 30 and 0 decibel milliwatts as shown in Figure 3.22. Table 3.2 summarizes the measurement characteristics of cascade LNAS. The main task of a power amplifier is to increase the power level of the input signal to a predetermined level. Unlike low-level amplifiers, the main characteristic of PA is the output power level. The section introduces a 1 watt power amplifier for CDMA using gallium indium phosphide gallium arsenide phosphide HBT technology. The power amplifier consists of a 3-level amplifier designed using K-Co's company's a 6-inch gallium indium phosphide gallium arsenide phosphide high linearity HBT technology, and using a vertical bipolar transistor model to extract large signal characteristics. The main task of power amplifier is to increase the power level of the input signal to a predetermined level. Unlike low-level amplifiers, the main characteristic of PA is output power level. The section introduces a 1 watt powered amplifier for CDMA using indium gallium phosphide gallium arsenide phosphide HBT technology. The design of power amplifier can use the same matching principles as small signal design, but the output requires power matching rather than conjugate matching. The design of a power amplifier is similar to that of a low-noise amplifier. The device must present power matching at the output end to extract maximum power. Power matching can significantly increase the compression power point and maximum linear power by 1 decibel. The load traction method is an empirical method for designing power amplifiers. Maximize output power by adjusting the output tuner, then measure the input impedance of the tuner, and draw a power contour map. And the load traction system is not only a design tool, but can also be used for extracting nonlinear models of active equipments. Figure 3.27 shows the max available gain and the S21 gain. The S21 gain is higher than 25 decibel milliwatts in the CDMA band. Figure 3.28 depicts stability in the band. In this bandwidth, the stable factor is over 1 and the power amplifier is stable state. Figure 3.29 shows the P1 decibel for 34.59 decibel milliwatts. Figure 3.30 shows the PAE as function of the input power. The fabricated three-stage PA is shown in the figure 3.31, and the third stage or last stage of the PA consumes significantly more current than either of the previous two stages. Therefore, bonding wires are used in the output parts, and the figure 3.32 is the PCB board used for measurement. And this is my presentation. Thank you for your listening.